Despite the extensive use of contemporary AC power systems, separately excited DC generators are still a crucial component in the field of electrical machines. They are highly relevant in laboratory settings, industrial processes, and specialized applications such as battery charging, electrochemical production, and excitation of synchronous machines due to their ability to produce DC output that is both stable and controllable. According to Adhikar in Podel 2021, in contemporary engineering education and specialized application, DC equipment continue to be crucial. Research over the last 10 years has concentrated on parameter identification, accurate modeling, and the integration of DC machines with advanced control systems and renewable energy sources. Battery charging, electroplating, traction systems, and synchronous machine excitation systems are examples of contemporary uses. The methodology used in this study is divided into two main types. First, we have the theoretical modeling, and the second one is the computational or experimental approach. This combined methods allows us researcher to analyze the performance, characteristics, and voltage behavior of the separately excited and DC generator, both mathematically and through numerical calculations. In the first part of the methodology, the researchers used the basic electrical equations that describes how a separately excited DC generator operates. This equation help explain how the generator produces voltage and how different factors such as field current, speed, and armature current affect its performance. So first equation that used is induced EMF. This equation shows that the generated EMF depends on the magnetic flux and the rotational speed because the field current in a separately excited DC generator comes from an external source. The flux can be controlled independently, which improves voltage regulation. The second one equation that is terminal voltage. So this formula is used to determine how much voltage drops through inside the generator when current flows through the armature. And the third one is the power equation. So these equations help evaluate how efficiently the generator converts mechanical input to electrical output. After establishing the theoretical model, the researchers performed numerical calculations to analyze how the generator behaves when the load current changes. This is done using selected parameters based on standard laboratory machines and published references. So first step is the selection of the parameters. Realistic and commonly used machine values were chosen to ensure that the results closely represents actual generator performance. The parameters used include, first we have armature resistance 0.5 ohms, and then generated MF, we have 240 volts. Load current that range 0 to 20 amperes and with a speed of 1500 RPM, which it is constant, and a field voltage of 220 volts with a field current of 1.5 amperes. So the rated terminal voltage we have 240 volts. So these values allows the researchers to simulate the atypical separately excited DC generator used in laboratories and industrial application. So the second step is the voltage computation. Using the terminal voltage equations, we have the terminal voltage equals the induced MF minus the armature current and the armature resistance. So the computed value shows how the terminal voltage decreases as the load current increases due to internal resistance loss. The results also demonstrate that the generators still maintain good voltage regulation, which is a major advantage of a separately excited generator.
Good day, everyone. I will now present the results and discussion of our research. We began by analyzing a numerical example using the given parameters. Armature resistance is equal to 0.5 ohms. generated EMF is equal to 240 volts and a current range from 0 to 20 amperes. The equation used for determining the terminal voltage is Vt is equals to E minus Ia times Ra. So based on the table, when the load current is 0, the voltage drop is also 0. So the terminal voltage remains at 240 volts. As the load current increases to 5 amperes, 10 amperes, 15 amperes, and 20 amperes, the voltage drop also increases. Because of this, the terminal voltage gradually decreases from 237.5 volts down to 230 volts at full load. This result shows that the terminal voltage decreases as the load current increases. So the main cause of this behavior is the ohmic losses in the armature winding. Even with this decrease, the drop is only around 4%, which means the generator still demonstrates good voltage regulation. Our research also emphasizes that a separately excited DC generator offers better control over the terminal voltage. The field current can be adjusted independently, which helps keep the output stable under different load conditions. These findings agree with the works of Adhikari and Podel at 2021, as well as Kumar and Singh at 2020, which state that separately excited generators provide better voltage regulation and more stable performance compared to shunt-excited machines. In practical applications, this type of generator is commonly used in battery charging, laboratory experiments, and excitation system for synchronous generators, all of which require a consistent and controllable DC supply. Overall, the small voltage drop shown in our results explain why separately excited DC generators are suitable for systems that need steady and well-regulated output. Now, let me move on to the advantages of a separately excited DC generator. First, it has better voltage regulation. Because the field winding is supplied by an independent source, the terminal voltage remains relatively constant even when the load current varies. Second, it provides a stable and predictable output. The generated EMF depends mainly on the field current and speed, both of which can be precisely controlled. This makes the generator ideal for applications that require steady DC power. Third, it allows independent control of field current. The field current can be adjusted without affecting the armature circuit, resulting in improved performance under different load levels and more flexible voltage management. Fourth, it does not rely on residual magnetism, since it does not depend on leftover magnetism to start voltage buildup. Its operation becomes more reliable. Fifth, it is highly suitable for testing and laboratory use. Because of its controllability, it is often used in research settings and educational institutions for machine testing and power electronics experiments. Lastly, it is useful in industrial applications. Its stable DC output is ideal for electroplating, battery charging, and excitation systems where a consistent voltage is required. So that concludes my presentation on the results, discussion, and advantages of a separately excited DC generator. Thank you for listening.
The separately excited DC generator presents several operational and economic limitations. First, it requires an external DC power source to energize the field winding, which increases overall system cost, complexity, and dependence on an additional supply. Second, the initial installation is more expensive than self-excited types because the system needs two separate electrical sources, one for the armature and one for the field. Third, like all DC machines that use commutators and brushes, it is prone to mechanical wear, sparking, and maintenance-related issues. Fourth, its efficiency is generally lower compared with modern AC generators paired with power electronic converters, which provide higher performance and lower losses. Lastly, the added circuit components for field excitation introduce more wiring and control elements, leading to increased maintenance requirements over time. In conclusion, this study shows the separately excited DC generators provide better voltage control and more consistent performance. This is because the field excitation is independent from the armature circuit, making the generator stable even when the load changes. The numerical example demonstrated only a small voltage drop, which confirms strong voltage regulation. This result supports previous studies from the past decade that observed predictable and linear behavior. Overall, the study proves that separately excited DC generators relevant in industrial, laboratory, and research applications. For future studies, these researchers recommend exploring digital control systems, testing different load conditions, and examining saturation effects for better design accuracy.